Everybody. So this is a little extra help session here for Kirchhoff's law, and this isn't lab one, actually. This is like the practice, so Kirchhoff's practice. So we have two examples here. We have a series example. So this is a series circuit, and down below here, this is our parallel example. Okay, so according to the notes, Kirchhoff's law states that in series, current is going to remain the same and voltage rise is equal to the voltage drop, okay, which means that all of the voltage is going to add up to the total. Okay, so I is constant, it remains the same. E is going to add up. Okay, so we need to know that portion of Kirchhoff's law in order to figure out the rest of this stuff. So the first thing we need to do here is solve for our circuit totals. Resistance total is equal to R1 plus R2 plus R3. So 1,000 plus 2,000 plus 3,000 is equal to 6,000. Okay, so my resistance total is 6 kilo ohms. My voltage total is this right here, okay? It tells me in this case that my voltage total is equal to 9 volts. We need to calculate for I still. So when we look at our circle here, we cover up I is equal to voltage, in this case, which is 9, divided by resistance, which is 6,000. I really cannot stress enough, like, we're doing all this work on the computers, but how important, like, a piece of paper and a pencil is really going to help you guys out with these problems, because you need to see your work, honestly. So we take our calculator and we say 9 divided by 6,000. We get this number here, which is 0.0015, okay? So that's 0.0015 amps, aka 1.5 milliamps. Okay, so that's really our answer right there, 1.5 milliamps. And because Kirchhoff's law says that I is constant, we're going to take that amperage and we're going to apply it to each of these resistors. So we have 1.5 milliamps for resistor 2, 1.5 milliamps for resistor 1, and 1.5 milliamps for resistor 3. The thing that adds up, the thing that we don't know right now is voltage, but we do know our resistances. The resistance for resistor 1 is simply like 1,000 or 1 kilo ohm. The resistance for resistor 2 is 2 kilo ohms, and the resistance for resistor 3 is 3 kilo ohms. Okay, so now we're solving for voltage for each one of these. So voltage, again, looking at our circle up here, voltage, I cover that up, is equal to current times resistance. So 1.5 milliamps, which again, we need to convert, so I already have it in my calculator, 0.0015 times 1,000 is equal to 1.5 volts. 0.0015, I'm putting that value, this value back in. Now I'm going to multiply that by 2,000 because again, E is equal to I times R. So my I is 0.0015 times my R, which is 2,000. So this is equal to 3 volts. And then 0.0015, my current times my resistance here, 3,000, is equal to 4.5 volts. So voltage rise is equal to voltage drop. If we say 1.5 plus 3 plus 4.5, that gives us 9 volts, which is equal to the voltage here. Okay, so they add up. We know that this is correct. They're also all in between 1 and they're equal to 1 or greater and less than 1,000. So they're in the proper metric prefixes. So we can be pretty confident that everything here is done properly. Okay. So putting my timestamp down here for later on, so that's done at 5 minutes. Anyways, let's move on to parallel. So when we go to do parallel here, parallel states that voltage is going to remain the same in parallel, while current is going to add up. Okay, so here our E is constant, while our I adds up because it's in parallel. So first of all, once again, our voltage is 9 volts. And as a matter of fact, because E is constant, we know that at every one of these, 9 is already our answer. We also actually know at this point what our resistance is for each one of these individual circuits, which is 1 oh no, I'm sorry, this is 1 kilo ohm. Resistor. Oh, it'd be helpful if I put the right resistor numbers on here, that's for sure. So this technically, I guess, should be resistor 4, this should be resistor 5, and this should be resistor 6. I'm sorry about that. Just label them anyway. As long as they match up, they'll be fine. So anyways, 4 is 1 kilo ohm, 5 is 2 kilo ohms, and 6 is 3 kilo ohms. Technically, we can already solve for I for each one of these, but we're going to come up with our circuit totals first so that we know. The resistance total in parallel is equal to, is equal to 1 over resistance total is equal to 1 over 1,000 plus 1 over 2,000 plus 1 over 3,000. So I go 1 divided by 1,000 plus 1 divided by 2,000 plus 1 divided by 3,000. That's equal to this decimal point, right? Remember, you're never going to see resistances less than 1 in this class, okay? So you know that this answer is not right yet. That's because you still need to solve for the opposite side of the equation, the 1 over RT. And for you guys to do that, you would say x to the negative 1. So if I say y to the x here and I say 1 negative, it's the same process. And that says here that my resistance total is 545.454545, on and on and on. So ideally, the more decimals you have here, the better off your answer is going to be. So 4545, going on and on and on. We need to figure out I. 9 divided by 545.454, oops. Then a 5 at the end here. I'm going to hit divide is equal to. So again, I took, because I'm coming up with I, and I is equal to voltage divided by resistance. So voltage divided by resistance here, I'm coming up with 0.0165 amps or 16.5 milliamps. I do like to write down my base number here so I can just keep referring to that to like stick it into my calculator. But this is the answer that like is required because it needs to be in the proper metric prefix, okay? So I like to write both for this. Same value, different metric prefix. So once again here, E is constant, so that's why we have 9 volts everywhere. I is going to add up. This plus this plus this should be equal to 16.5 milliamps. And like I already said, technically you didn't even need to figure this out first, but the advantage to this is that the voltage we can check, and make sure that things work right. So again, when we look at this, we have E over I times R. So here we're looking for I. So I is equal to voltage divided by resistance. So for this one, we have 9 divided by 1,000, 0.009 or 9 milliamps. The next one, we have 9 divided by 2,000, which is equal to 0.0045 or 4.5 milliamps. And then lastly, we have 9 divided by 3,000, which is equal to 3 milliamps. And remember, amperage is the amount of electrons that pass through a point in a given second. And also remember that electrons are always going to take the path of least resistance. So it makes sense that the resistor with the lowest resistance also has the highest amperage because more electrons are going to go through that easy resistor than the others. The resistor with the highest resistance is going to cause the least amount of electrons to flow across it, which is going to lead to the smallest amount of amperage. Okay, so here we have 9 amps, 4.5 plus 3, right? So 9 plus 4.5 plus 3 is equal to 16.5, and in this case, milliamps is my unit. 16.5 milliamps. They add up there. Okay? That is the process for calculating Kirchhoff's law and the amount of resistance or I'm sorry, voltage or current that each one of these is going to be using. You can use this lesson to help you with Kirchhoff's law, Lab 1.